X radiation was discovered in 1895 by German physicist Wilhelm Röntgen. X radiation is a source of electromagnetic radiation that travels at the speed of light, just like any other source of radiation. It travels through a vacuum, and the given electromagnetic spectrum shows you exactly where X rays occur. X ray diffraction is still the traveling of X radiation. However, diffraction is the X radiation's interaction with molecules as it passes through a crystallized molecule. It was discovered in 1912 by Max von Laue, the German physicist, and by German physicist William L. Bragg was the Bragg equation, which just shows you mathematically the nature of these traveling X-rays as they diffract. Delta R shown in the equation shows you the difference in the distances traveled by these diffracted waves. And of course, theta in the equation shows you the diffraction angle of these traveling X-rays. Now, along with that X-ray diffraction is X-ray crystallography, which is the instrumental technique used with X-ray diffraction. And what I'm gonna do right now is I'm showing you the schematic flow diagram of X-ray crystallography, and I'm gonna go through each component of X-ray crystallography and explain exactly what they mean. X-ray crystallography, it's important to note that it was first commercially designed in 1945 by Phillips and Norelco. Now, radiation, the initial source is usually copper, because copper gives you an radiation of X-rays at its wavelength shown on the electromagnetic spectrum. And this pathway of radiation goes through a filter, which is usually just a monochromator, just like any other monochromator found in any spectrometric technique. Now, the diffraction of this beam, which explained earlier, was a source of radiation by copper. The beam is diffracted as it passes through the sample. D sub 1 shows you a clear example of a diffracted beam, and of course you always have a transmitted beam that travels through the sample. The sample is usually a crystallized molecule. Now, the diffracted beam, as explained earlier, is produced by a crystallized molecule. The diffracted beam goes on to the detector, which is usually a Geiger counter. One fun fact about the Geiger counter is they're also produced handheld now, which is used for ionizing radiation, sometimes beta decay. X-ray crystallography has now been explained to you from the description from a schematic flow diagram. Now to talk about where in research is it used. It's used in a paper that was actually just published last year in a research article on the computational modeling of the mechanism of urease. Urease, as you know from the suffix, is an enzyme. It's a hydrolytic enzyme, usually found in jack beans and bacterium, and it's found in the hydrolysis of urea into volatile ammonia and carbon dioxide. Now, what was analyzed about urease was this stepwise hydrolysis mechanism. The intermediate energies of each intermediate form, which was a total count of 8 intermediates, were analyzed. And one of the main structures that was analyzed was the fourth intermediate, which was a tetrahedral intermediate. The tetrahedral intermediate, the structure can be found in between the two nickel ions, which are highlighted in yellow in the image shown to your right. Now, the results in this research was showing the purpose behind the unique structure that was formed, well, all of the structures that were formed. How was the stability of each intermediate analyzed? And this is where X-ray crystallography comes into play. You had two methods used, which you can see X-ray crystallography in the computational model. And these two methods were actually compared to each other. as they were compared to each other, one thing to note about X-ray crystallography was that it was a drawback to it, which was it was slightly insufficient of locating hydrogen atoms, which is always one drawback to X-ray crystallography. Now, with X-ray crystallography, with that said about its drawback, that's one thing that's actually being studied. That's one thing that's actually trying to be improved about X-ray crystallography. Besides the fact of it being slightly insufficient of locating hydrogen atoms, it's shown it serves a good purpose in the following areas of science: organic chemistry, drug synthesis, which goes hand in hand with organic chemistry, biochemistry, and biophysics. The following information presented is not mine. If you're interested more in X-ray crystallography or the publication of this research article, you can follow the references shown below. The reference in red, both in red font, is the actual research article itself. Feel free to go to that whenever you want. I'm Jordan Lightfoot, discussing X-ray crystallography on the computational modeling, the mechanism of urease. I'm a student at Georgia Southern.